Hey, it's Miss Murphy. Hi, how are you? We're going to do a quick little lesson on resonant structures and formal charge, okay? Resonant structures, let me share my screen here. You're going to have a resonant structure when you're drawing Lewis structures and you start creating multiple bonds. And you can put those bonds in more than one location, then what you have is something called resonant structures, okay? And we're going to understand why they use the word resonance. And all of this stuff is important. It gets really particular. So you can't just be like, oh, I know it, and move on. There's things I'm going to tell you that you need to hear, okay? So let's look at, I think it's NO3 negative. I think this is going to give us a resonant structure. All right, so let's count our electrons. 5 plus 18 plus 1, because we've got that negative charge. That gives us 19 plus 5, which gives us 24 electrons available for bonding. Let me look at NO2 negative. Okay, no, that's good. I'm sorry. For a minute, I thought this isn't going to work, but I think it is. Okay, so let's put nitrogen in the center and let's arrange our oxygens the way they may be, right? Let's connect them and start using all of our 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, we just used all of our electrons. We're finished. We have no more electrons. So what I notice is that each oxygen, each oxygen has 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. So they're, satisfied. We've satisfied the octet. However, if you look at nitrogen, you will see that nitrogen does not satisfy the octet rule, right? Because currently we've only got the 2, 4, 6. So what that means, you should already know this, is that one of these oxygen atoms needs to form a double bond with nitrogen. Okay, so then students are always saying, well, what does it matter which oxygen forms the double bond with nitrogen, right? Because one of them is going to form a double bond. Well, it could be that this oxygen atom. And don't I need to put brackets around this with a charge because it's an anion? Actually, just because it's an ion. Well, the whole point is that double bonds will resonate between all of these oxygens, okay? So the double bond is not in one location the whole time. We don't just get to pick an oxygen nitrogen bond and make it the double bond, because that's not the way it is. In reality, we see that this double bond resonates throughout each of the 3. Let me finish this one up, okay? Finish it up and put the charge out there. What we see is that this double bond resonates from between each of the 3 nitrogen and oxygen bonds. It is not static, okay? And that's important because if I want to know the bond order of the nitrogen-oxygen bond, right, this is a first order because it is a single bond, right? This is a second order, okay? And this would be a first order. And we could continue that through each of the other molecules. And we'd have the same, just the second order bond would be changing locations, okay? Now, what it's important to note, because you'll have questions that come at you and students you don't know if you don't listen to me right now, is we have discussed that a second order bond is shorter and stronger, right? So therefore, in the first molecule, let me get rid of these highlights right here. In the first molecule, this particular oxygen double bond site would consider to be stronger than the other bond sites, right? And in this one, we would think it there and there. Well, that's not true because the double bond doesn't stay there. The double bond resonates. So what we have here is a bond order of 2 + 1 + 1, because they're all identical bonds, which is a 4 divided by 3, okay? Because it is spread in 3 domains. What's 4 divided by 3? Is that like 1 point? I don't want to embarrass myself. 1.33. Okay, so we have got a bond order of 1.33 here. Now, so what that tells us as well is that each of these bonds, all right, I'm going to put a cross through this. I'm going to cross this out. Well, let me undo that. I need to clarify this. However, the double bond resonates throughout, right? The double bond resonates. That means it moves around throughout each of the bonding sites. So resonates means to move around, okay, throughout each of the bonding sites. And because that double bond is resonating throughout each of the bonding sites, they are all, right, so there's my therefore signal. All bonding sites, and when I say bonding sites, I'm talking about the identical ones, the nitrogen, oxygen, hold on, let me rewrite that. I'm talking about those nitrogen-oxygen bonds, okay? Those are my bonding sites, the nitrogen-oxygen bonds. And because the double bond resonates through all of them, they all have, right? Therefore, right, here's my writing. Therefore, all bonding sites have equal length bonds, and equal bond energies. Okay? And you have to know that, in equal bond energies. Very likely to pop up in the course of this content, especially with, you know, the AP course. Okay, so that's your resonant structures, all right? And you see how to identify when you have, a resonance structure, right? We have more than one essentially identical structures, okay? All right, now we're going to introduce, and hold on, back to those resonance structures. You realize that the multiple bond resonates throughout the bonding sites. They're all identical. One is not stronger than the other. But so each nitrogen and oxygen bond here is actually stronger than a nitrogen oxygen single bond, but weaker than a nitrogen oxygen double bond, because it's in between, right? Because it's not a bond order of 1, and it's not a bond order of 2. It is a bond order of 1.33. So it's stronger than the single bond, but it's weaker than the double bond, this nitrogen and oxygen bond. Okay? All right. Now let's look at another concept. And this is the concept of formal charge. Okay? Formal charge. And when do we apply the concept of formal charge? Now listen to me. Okay. When there is more than one, I'm going to write applied when. So go ahead and start writing that. Applied when, applied when there's more than one correct Lewis diagram. Applied when more than one correct Lewis diagram can be drawn. Okay. And I'll give you an example. And we use, it is used to determine the correct Lewis structure, correct/actual Lewis structure, okay? And what we want to do, so we see when we use it, why we use it, what it's going to give us, and now the question is, well, how do we use it? Okay, well, formal charges, you don't necessarily have to write all this. Formal charges are applied to all atoms, okay? There's a formula for it. It's just a little subtraction. We want, ideally, the most electronegative atom has the negative formal charge, and that's assuming there is one. All right, so I will clarify that and say if there is one. Right, there's not necessarily anything that's going to have a negative formal charge. If there is one, so I probably should have, if there is an element with a negative formal charge, it needs to be the most electronegative element in the compounds. Okay, so ideally the most electronegative atom or element in the compound has a negative formal charge, if there is one. And ideally, all formal charges are as close to zero as possible. We want to minimize the magnitude of those formal charges. So that's zero as possible. What that means is, you know, ideally, I'm writing too much, we minimize the magnitude of formal charges, okay? So that's how we have these, and we'll do an example. We'll have multiple Lewis structures, and then we'll apply formal charges to say, well, this one's a better Lewis structure. And we'll look for the lowest formal charges, and if there's a negative, is the negative on the most electronegative atom. If not, then it's not a really good Lewis structure, okay? So how do we get a formal charge? We take the number of valence electrons, I wish I had more room for that. I wonder if I could turn my screen. It doesn't really want to give me much space. Number of valence, I'm going to rewrite it. Number of valence electrons. Now, it's the, okay, we're going to subtract from that 1/2 bonding plus non-bonding electrons. It's easier just to tell you. All right, so let's show you an example, okay? So let's do CO2 with a triple bond and a single bond. I'm gonna clean that up a little bit. And if I haven't said, you have to draw the electrons, okay? You cannot get, no, this is not a resonant structure, guys. This is just two different ways to draw the same, to satisfy the octet. Now, this one's gonna have the two double bonds. What you're gonna see is that often the best structure doesn't satisfy the octet. So you're gonna realize these are models, these are man-made models to help us understand and explain, and they work to explain things, but sometimes our predictions are not actually correct based on the models that we created, okay? So you're gonna see that sometimes it's a different Lewis structure than you would have thought. Okay, not in this case though. So let's assign formal charges. So what the scenario is you're faced with two Lewis structures for carbon dioxide, both of which use all of their electrons, both of which have the octet satisfied for all atoms, elements involved. So we're going to assign formal charges to determine which of these is the better structure, and then we can use those as evidence for our claim, okay? You have to remember to use it for evidence for your claim. So I know that oxygen has 6 valence electrons And right now, let me show you how to count them. 1, 2, 3, 4, 5, 6, 7. 1/2 of the bonding site, okay? So 6 minus 7 equals -1, right? Carbon, let's give him a different color. We'll make him red. He's got 4 valence. And we're gonna go 1, see it was 1, just half, 2, 3, 4. Okay, so 4 minus 4 equals 0. You'll see that happen a lot. Now let's do oxygen. I'll get another color here. He's got 6 valence electrons minus 1, 2, 3, 4, 5, minus 5, and that's a positive 1. Okay, well, let's do the same for the other. And so let's start here. He's got 6 valence electrons minus 1, 2, 3, 4, 5, 6. So that equals 0. Carbon here has 4 valence electrons minus 1, 2, 3, 4. So that's 0. And then the other oxygen here has 6 valence electrons minus 1, 2, 3, 4, 5, 6. So that gives us a formal charge of 0. So this is a no-brainer, right? We've got formal charges of 0 for all elements when the Lewis structure looks like this. So this is our best Lewis structure. He is the winner, okay? And notice, you know, we don't need to worry about the negative rule because there are no negatives here. But because all formal charges are 0, this is going to be our best structure. Let's look at another one, SO42 negative. All right. This is 6 plus 4 times 6 plus 2. This is what, 24 plus 6 plus 2 equals 32 electrons. All right. Okay. So I'm going to go ahead and bust it out because I know what's going to happen. All right. So that's my 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Boom. Okay. Now, there's another structure that could be drawn. It looks like this. Okay, so you could be asked which is the better structure and why. All right, so you've always got to defend your answer, and some of you are really good at doing that, and some of you are really lazy. And you've got to provide proper defense for your answers. You won't get credit. All right, let's go ahead and assign some formal charges real quick. Each of these oxygens, each one of them, right? All of them are identical. I see 2, 4, 6, 7. So it's 6 minus 7. I've got a -1, -1, -1, -1. And for sulfur, I've got 6 minus 4, which is +2. Not looking good. Well, here for this sulfur, I've got 1, 2, 3, 4, 5, 6. That's 6 minus 6. That's 0. I've got a -1, -1. And I'm doing this fast now. I've got a 0 and I've got a 0. So the magnitude of charges in this one, this second, excuse me, come on. Oh, sorry. I've had problems. Y'all don't see. The second one actually has the lower magnitude of charges because there's just a negative, and it is on the most electronegative element, so that's cool. Sulfur is not more electronegative than oxygen, and these are zeros. Then when I compare that to the negative and the negative and the positive and the negative and the negative, overall, these are closer to 0. Okay. So this is actually our preferred structure. Now, listen to me. When you are asked to draw a Lewis structure, you do not need to consider formal charges. You need to satisfy the octet rule. So yours would look like this. If draw it for sulfate, they're probably not going to ask you for this reason. Your job, for me, for AP, I'm telling you, I know these things, use the octet rule. Your job will be to be able to use formal charges to pick the best structure when they are provided to you. They will provide you with multiple structures. And then you apply formal charges in effort to figure out and support why one structure is better than the other. Okay? You don't need to consider formal charges when you yourself are drawing your structures. That is the rule for this course. Okay? And that's it. That's it. So you obviously you have to work with it because things can get confusing. That's my experience. So things can get confusing. You know, we talked about resonance, then resonating, getting the bond order related to the bond length and why one is not stronger than the other, but they're all the same. Okay, so that's your resonance structures. You do need to draw all resonance structures when it applies. Okay, and you need to make sure you show all your electrons. All right, great. Thanks. I'll see you soon.